morning, my dear students. Last week, you went through the topic trigonometry. And I believe that as at now, you have that better chance of tackling vectors. Before we move on, I would like to take you through the objectives. Students should be able to differentiate between vector quantity and scalars. The point number 2, students should be able to perform operations on vectors. And lastly, students should be able to apply their knowledge to solve real-life situations. What therefore is vectors? When we talk about vectors, I want to demonstrate something. If you are asked to move 2 steps, somebody will just move backwards. 1, 2. The person is right. To another person, he may take it sideways, like 1, 2. Yet another person will then move forward. Any of these is considered to be correct. Why? Because no direction was given. Vector is therefore defined as a quantity with both magnitude and direction. Let us consider this. If a car is moving, we most often than not consider the speed. Now, if you consider the speed, you see that there's no direction attached. Once you attach direction, then it changes from the speed to what we call velocity, which is an example of a vector. If, like I told you, to take 2 steps, it's just a distance. But if you are directed that move forward, then it changes from just the distance to what we call displacement, which is an example of a vector quantity. So, talking about vector quantities, we can have as examples displacement, we can talk about velocity, we can talk about acceleration, momentum, just to mention a few. Now, let me send you back to scalars. Scalar is a quantity with only magnitude. For example, if you are asked to take your room temperature, here no direction needs to be attached. So that would be an example of a scalar quantity. Talking about distances without any direction, the example of scalars. If you are asked to take the time or the duration as to when a tap will fill a container, that time. If you are to take the weight of a body, mass. So, this to help you, as I stated in the first objective, to be able to differentiate using real life situation. Having talked about the definition for vectors, it's important that we talk about how it's being represented in geometry. And here, in simpler terms, I would say in diagrams. A vector is represented by a directed line segment. What I mean by directed line segment is any line segment drawn with arrow on it. Now, the length of the line gives you the magnitude of the vector itself. And where the arrow points also gives you the direction, making it a vector quantity as such. Now, look at the drawings that I've indicated on the screen. Can you name them if you are asked to name them? How is that done? A critical look at them, at the diagram, will show you that we have a starting point and a terminal point if you follow the sense of direction of the arrow. So in naming, that is the way to go. The starting or the initial point should be mentioned first. Then the terminal will follow. So can you name the first one for me if I'm to take you back? The first one. Can you do it for me? Yes. You've done well. You see, the first one is vector AB, because the initial point is A and then the terminal is B. Yes, who will try the second one? Yes? Are you sure of what you are saying? Yes, you've done well. The second one is vector TP, because the initial point is T and the terminal point is P. Very good. Let's move to the next point. Forms of vectors. We can talk about three basic forms. And these are namely the column or component form as one. The second one is the magnitude and bearing form. Then the last but not the least is the Cartesian or standard basis form. If you watch well, you see one thing for yourself. Now for the second form, you clearly see the magnitude, 5 meters, then the direction in terms of angles, or better still, bearing, as 030 degrees. So it has magnitude and then what? Direction. Now, if I may sketch it on the board, you see it this way. Yes, as you can see on the board, a vector of length 5 meters with the bearing 30 degrees. That is one example of it. Now let's move to the first one. The first one talked about the column or component form. And I've clearly indicated you have vector AB as x, y. Right, where the x and y are what we call the components of the vector. The content of it is called the component. The x, as the name implies, is what? X component, because it's measured along the x-axis. So, look at the board. There's your x-axis. If I want to there, assuming we have x1 is going to take this 4 against y the second one it will also take that direction. So the vector we are talking about will start from here and end there. That is what we mean by a vector in the column 4. It's important that we learn how to draw or sketch this on a sketch pad. And I believe that you can do it. The only thing to consider is that when you pick, let me send you the board. On the Cartesian plane, like this, you have your x and then you have your y. Right. So this is the origin. To your right, we have positive, and then to your left, we have the negative numbers. Okay, looking up here, from the 0 upwards, we have the positive side, and then downwards, negative. So, as we have on the board, let me show you something I've prepared. Okay. So, giving you vector OA as 3, 4. Vector 3, 4. What you have to do is that you have to indicate, and you know it must be 3, 4. Okay, so looking at 3, 4, the 3 is positive. Definitely, we move 3 steps from the origin. On the x-axis, because that's the x component. Then 4, because it's positive, we move up. If we were to be negative, we have come down. So we move up 4 steps. And then your vector will be where you started up to where you ended. That is your vector OA for the column 4. Looking at it, the examples, I think it's quite easy to come out with your own examples. For example, if we are to give you this, let's see, you have a vector OR. Right. Let me give you the component as neg 1, neg 3. Right. What happens is that you will consider this the top on the x-axis. So neg 1, from here you move. And because it's negative, we continue downwards. Hence, your vector is this. I believe that you can also do your own examples. Very good. Having talked about these things, it's important that we talk about, the length of it. How do we know the length of a vector, especially when it's given in component 4? Remember last week, you talked about Pythagoras Theorem. And here is the best stage to apply. Now let's consider again. The vector OR with the component 3, 4. Again, you see something. If it's to be represented on the Cartesian, let me graduate it. Sketching. What happens is you have look at it well. You see, you have a right-angled triangle, and here we are to find the longest side, which happens to be called the hypotenuse side. Meanwhile, the other two sides has been given. And what does the Pythagoras Theorem says? You only did that last week. Can you try it? Good. Let me repeat it for you. We said that in a right-angled triangle, the longest side square equals to the sum of the squares of the other two sides. Okay, so looking at this, to find my OR, my OR square will be given as 3 square plus 4 square. Is that not it? Yes. Good. So that the length OR becomes the root of, this plus that. So you have 9 plus 16, which is 25. And the root of it will be what? 5 units. Good. That's how you can what? Find the length. Good. So if you look at what is on the slide, you notice it. That our formula is then given as our AB, the vector, is given as the square roots of what? S squared plus what? Y. So if you are given any vector, this is what you do. You just take the components, square them, sum them up, and take the root of it. I hope you are clear with this point. Good. But if you are to consider the diagram still, there is one interesting thing. We can find this angle. Good. Because remember, that talking about vector, we deal with the length and then what? The direction. So this will help us. And from what you did under SOHCAHTOA, which is talking about what? The sine, talking about the cosine, talking about the tangent. You learn something. Here we apply the tangent. The tangent of the angle here, tan theta, will be equals to the opposite side on the adjacent side. Very good. So this can be calculated. This is to tell you that we can change from one form to the another. You're looking at this. If the form is component or column form, you can be asked to convert to magnitude and then what? Bearing form. We'll talk more about that later on. That's right. Now with this, we move to operations of vectors.